At the moment, the method we use for loading a program into the computer is not very efficient. So we want to change the input-output method. Now, as it stands at the moment, what we do is we load a program into this external RAM, and then we load it from the external RAM into this internal RAM here, and then we run the program. But what we want to do is we want to get rid of this internal RAM here, and we'd like to place this internal RAM on the top level. But we'd also like to replace that internal RAM with an actual RAM block like this, because it will run an awful lot faster and be a lot more efficient. So in this video we're going to look at this input-output method, which will allow us to get rid of this. It will also allow us to get rid of this counter here, which we use to count in the program into the RAM, and it will allow us to get rid of this RAM block here. So let's go ahead in this video and we'll see how to design this input-output. Now, if you've built up the circuit from the first course, you'll notice that we have 4 other pins here that we haven't used. We've got an S and an E, so that's set and enable, and we have an I, O, so that's input-output, and D, A, that's a data and address. So we actually have the circuit already designed into the control unit, we just haven't used it from the previous course. Now, if you haven't already built this circuit in, then don't worry about it. We'll explain that circuit through the rest of this video. But you'll see here that if we were to get into the control section, you'll note that we have the bottom AND gate here. Now, we never described the bottom AND gate in the last video series, but this bottom AND gate is going to be used for our input-output. So you can see that there's a couple of other AND gates connected to it here, and that goes up and it goes to a couple of different points throughout the control unit. So we'll go ahead and we'll describe that now. Now, the first thing to note is that in order for this AND gate to go live, we're going to have a 1, 1 and 1 in our 3x8 decoder. So these come from points 4, 5 and 6 on the instruction register. So whenever 4, 5 and 6 pins in the instruction register go high, then we know we're going to be using an input-output, and also the 7th one here would have to be a 0. So let's go ahead and the rest of this video and we'll describe this new instruction and how it works. So this is our new instruction. Now, this instruction allows us either to send information to the outside world from the CPU or receive information from the outside world into the CPU. So it tells us whether we're going to push information out or get information back in. Now, if we're going to get information from the outside world, we have to get it from somewhere. So let's say, for example, we could have an input device, and that input device would be, for example, a keyboard or a mouse. So the computer, the CPU, is receiving information from these devices into the CPU. But these devices, we would have to be able to distinguish one device from another. So we would have to have an address for each of those devices. So for example, the keyboard could have address say 00000001, and a mouse could have an address 00000010. So that would be address number 1 and address number 2. So we would have, in order to get information into the CPU, we would have to ask, first of all, where is it coming from? And we would get that from an address. Also, if we were passing information from the CPU to the outside world, we would have to say, where is it going to? And it would go to that address. Now also we would have to decide whether there's actually data coming in or an address coming in, or whether it's data going out, an address going out. So these are the four options here that we're going to have. We're going to have an input of data, or an input of an address, or an output of data, or an output of an address. Now, where is the information containing the data or the address coming from? Well, they're going to come from register RB. And register RB is going to be obviously a value for register 0, 1, 2 and 3. So you can see here the rest of the instruction. This bit here controls whether it's an input or output, so that's a 0 for output and 1 for input. And this controls whether it's a data or address, so data 0 and address 1. And these two bits control which register we get the address or data from. So finally, I've just written it down in this little truth table here. So this first column here is going to be the I/O, and the second column is going to be the data or address. So if we get 0, 0, we know we're going to input data. If we get 0, 1, we know we're going to input an address. If we get 1, 0, we know we're going to output data. And if we get 1, 1, we know we're going to output an address. Now don't worry too much if this seems unfamiliar to you. We'll have a look at the circuit and see how it works. And once we build it up and we test it, it'll become obvious how it's all working. So here is a representation of the input-output circuit. Now I already have this built within the control unit, but it's much easier to show you this simplified representation than it is to describe it within the control unit. So we're going to have our instruction register here. We've got our 3x8 decoder, which chooses our instruction. And we're going to have our counter or stepper, which has the fetch cycles 1, 2 and 3 and the execute on cycles 4, 5 and 6. Now for the input-output, we only use the stepper at sections 4 and 5. I've also put a truth table here as a reminder of the values for our input-output data and address. We know it's going to be an input-output instruction if the bytes 0, 1, 1 and 1 occur. And we know the reason why that is, because if we have a 0 here on this bit, it means that we're going to have a 1 here, which ensures that we're going to choose one of these instructions. If it was a 1 in this bit here, then we would have a 0 here, and we would have a line that passed off from here, and we would have an ALU instruction. Now we're going to have the 1, 1 and 1 because we know the instruction that we're going to choose is the bottom instruction here. Now we're going to have two possibilities. Either we're going to have an output or we're going to have an input. And the output and the input is determined by steps 4 and 5. So if we look at the truth table here, we can see that we're going to have an output whenever we have a value of 1 on this bit here, which is the 4th bit. So when we have a 1 here, we know we're going to have an output. So this point here, the stepper through this AND gate, is going to control the output. Now, if we had a value of 0 on that bit, then this line here would be low, therefore this line here would be high, and it would be step 5 that we would be interested in, and step 5 would control the input. So we're going to have output here, and we're going to have input here. Now, Is the output and input going to be an address that you're outputting or inputting, or data? Well, we're able to tell that from taking a copy of the lines 3 and 4. And lines 4 is the input output, and lines 3 is the data address. So let's follow the first one here, which is going to be our output. We can see here that the value for IO has gone to a value of 1. So this line here, which is line 4, will have gone to a value of 1. So we would have a 1 here. And we know that we're going to be using an IO instruction whenever we get the 0111, and therefore this line here would go high. Now all we need is to wait for the stepper to pass over to step 4. So when we get step 4, we're going to have all these 3 conditions are going to be met. Now, when those conditions are going to be met, we know that we're going to have an output. But where does it get the information from that we want to output? Well, the information must be sitting in one of the registers. So we have a reg B gets enabled. So we have the information we want to pass out in one of the registers, and then we enable that register onto the bus, so it's available to the outside world. So now, once it gets enabled onto the bus, we're going to have to clock that information out of the CPU and into a device. Now, in order to do that, first of all, we would have to know which device we're going to be using. So we would have to output an address. And once we have decided that that's the device that we're going to talk to, we send out, in effect, a little address out to that device, which really says to that device, we're going to use you and we're going to output our data to you. So it has to know it's going to receive that data. Now, it works out that it's going to receive that data from this little line here. So we have this little line here coming out, and it's going to be the IO clock set. So this is going to pass out to a particular device a little set pulse. So the set will go high and then it'll go low, and at that point that device will have been chosen. Okay, now you'll see that whenever we build up the actual circuit, but we won't get to the circuit until the next video. Okay, so that's what happens whenever we output an address. But once the address has been outputted, we know that we can then go ahead and we can output the data to that device. So we would then go ahead in the next step and the data would pass out to the device. So how does the device know it's going to be receiving an address or whether it's going to be data? Well, we're going to have a copy of all the lines here. So we'll have a data and an address, and we'll also have input output from pins 3 and 4. So those head out to the outside world. Now the other option that we're going to have is we could have an input. So we know we're going to get an input whenever we're going to have 0 on this line 4. So when we get a 0 on this line 4, we can see here it heads up here, and that 0 comes along and it goes through this inverter or the NOT gate, and we get a 1 here. Okay, so this ensures, this little NOT gate ensures that we can't use both of them. We can't do input and output at the same time. We're just going to use either an input or output or an input. So whenever this goes high, we're waiting for step 5. Now when step 5 comes along, we know from this line here, which is copied down here, that we have requested an input output. So that means that all 3 of these lines here would then go high. So when all 3 of these lines go high, what we're going to do is we're going to receive information into the CPU. So that is, we're going to receive information into one of the registers. So it's going to be Reg B, and it's going to be either 0, 1, 2 or 3. So we're going to have to set that information into the register. So the set will go high and then low, and that information will be set into that register. And again, we're going to have to clock that information in. So we clock it in via this line here, and this is the clock enable, and this goes out to the IO clock enable. So that's the route we're going to take, and that's the circuit we're going to build. But I'm not going to do it in this video because it's getting too long now. We'll go on the next video, we'll actually build the circuits. So not only do we have the circuit here within the control unit, we're going to have to create a couple of input and output circuits in order to test this. So these input-output circuits, in effect, we're only going to input and output just single bytes, but they could represent keyboard, a mouse, or a screen, a VDU, or any other input-output devices. And we're going to see how we are able to address each of those devices individually. And it's quite smart, and it's quite nice, and it'll make the rest of our design of the CPU a lot simpler. Don't worry if you're not getting all of it, it'll all become apparent when we get to the next video and we build up the circuits and get it working. So thanks for listening, I'll get you in the next video. Goodbye.